In this video, we will be discussing global climate systems. Several components of the energy-atmosphere system work together to determine Earth's climates. The two principal climatic components, temperature and precipitation, together reveal general climate types such as hot and dry tropical deserts, cold and dry polar ice sheets, or warm and wet equatorial rainforests. In this slide, worldwide average precipitation is shown. Notice how the patterns on this slide reflect factors that you are probably now familiar with, including temperature, air pressure, air mass types, atmospheric lifting mechanisms, and solar energy availability, which decreases from the equator to the poles. The climate in any location results from the complex interrelationships between several factors, including insolation, Earth's energy balance, temperature, air masses, air pressure, and atmospheric moisture and precipitation. These factors are key to understanding Earth's diverse climates. The climate classification presented in this slide is a modified form of the Köppen system. The map portrays the geographic range of various climates, including tropical, dry, mesothermal, microthermal, and polar highland climates. Temperature and precipitation characteristics are the main factors that determine these climates. Also shown on this map are selected atmospheric and oceanic circulation patterns that modify the various climates. The patterns include air masses, ocean currents, air pressure systems, and the January-July locations of the Intertropical Convergence Zone. In this video, we'll look in closer detail at each of these climate classifications. All tropical rainforest climates are consistently moist and warm. Convectional thunderstorms, triggered by local heating and trade wind convergence, peak each day from mid-afternoon to late evening. Precipitation follows the migrating ITCZ northward and southward with the summer sun. Water surpluses are enormous, creating the world's greatest stream discharges in the Amazon and Congo river basins. High rainfall sustains the lush, broadleaf evergreen tree growth of the Earth's equatorial and tropical rainforests, like we see in this image here. This slide shows a climograph for a city in Brazil that is a good example of a tropical rainforest climate. On the climograph, we can see that the lowest precipitation month receives about 6 inches of rain. In the tropics, the day-to-night temperature range exceeds the annual monthly temperature range. And the only interruption in the distribution of tropical rainforest climates across the equatorial region is in the highlands of South American Andes and East Africa, where cooler air at higher elevations produces some lower temperatures. Next in the tropical climates, we have tropical monsoon climates. Monsoons are seasonal rains produced by shifting winds associated with changing atmospheric pressure patterns. Rain brought by the ITCZ and the monsoon falls in these areas from 6 to 11 months of the year. These climates are mainly along the coastal areas and experience seasonal variation of wind and precipitation. And the final category for tropical climates is the tropical savanna climate. The tropical savanna climates lie poleward of the tropical rainforest climates. The ITCZ reaches these climates for about 6 months or less of the year as it migrates with the summer sun. Summers are wetter than winters because convectional rains accompany the shifting ITCZ when it's overhead. Temperatures vary more in tropical savanna climates than in tropical rainforests. The tropical savannas can have 2 temperature maximums during the year because the sun's direct rays are overhead twice, before and after the summer solstice in each hemisphere as the sun moves between the equator and the tropics. Grasslands with scattered trees, drought-resistant to cope with high variable precipitation, are what we see in the tropical savanna regions. Our next climate category is the mesothermal climates. These are the mid-latitude climates or the temperate climates, and they are categorized by having increasing variability of day length and insolation. They have shifting maritime and continental air masses. and these are guided by the upper air westerly winds. Their precipitation has variable results from the migration of cyclonic or low pressure and anticyclonic or high pressure systems, and these bring changeable weather conditions and air mass conflicts. And these climates also have variable sea surface temperatures that can impact air mass strength. So, cooler temperatures along the west coast can weaken air masses, while warmer temperatures along the east coast can strengthen air masses. The mesothermal climates are humid except where subtropical high pressure produces dry summer conditions. These mesothermal climates are divided into 4 different regions, including the humid subtropical hot summer, humid subtropical winter dry, marine west coast, and Mediterranean dry summer. This is an example of a humid subtropical climate. The humid subtropical hot summer climates are either moist all year or have a distinct winter dry period. In the summer, warm and unstable maritime air produces convectional showers over the land. And in the fall, winter, and spring, maritime, tropical, and continental polar air masses interact, and then this causes frontal activity and mid-latitude cyclonic storms. The abundant moisture and long agricultural growing seasons of these climate regions sustain the largest human populations on Earth. These are mostly concentrated in northern central India, eastern China, and the southeastern United States. Here's an example of a marine west coast climate. The marine west coast climates have mild winters and cool summers, and they are characteristic of Europe and other middle to high latitude west coasts. So cool, moist, and unstable maritime polar air masses tend to dominate these climates. Weather systems forming along the polar front and maritime polar air masses move into these regions throughout the year. So finally, in our mesothermal climate category, we have the Mediterranean dry summer climates, and this will be familiar to those of us in class living in the San Diego area. This is the climate that we live in. The criteria for a Mediterranean dry summer climate specifies that at least 70% of annual precipitation occurs during the winter months. And this is in contrast to the precipitation patterns in most of the world where summer maximum precipitation is normal. This climate occurs in only 2% of the Earth's land surface, along with the western margins of North America, central Chile, and the southwestern tip of Africa. And there's a few of these in southern Australia, as well as the Mediterranean basin. Next, we have our microthermal climates, or our mid-latitude and high-latitude climates with cold winters. So the microthermal climates are cool temperatures, and they have winter seasons with some summer warmth. About 21% of the Earth's land surface is influenced by these climates, and they're almost all entirely in the northern hemisphere. Temperatures decrease with increasing latitude and towards the interior of the continental land masses. So the result is that these patterns of intensely cold winters occur. So the factors that help to determine the microthermal climates are increasing differences in day length and seasonality due to increasing latitude. Also, increasing latitude results in decreasing sun angles and highly variable day length. Precipitation results from cyclonic air mass conflicts in winter and convectional thunderstorms in the summer. Microthermal climates have 4 distinct regions. These are humid continental hot summer, humid continental mild summer, subarctic cool summer, and subarctic with very cold winters. About 11% of the world's population lives in these microthermal climates. This is an example of a humid continental hot summer climate. The distribution of annual precipitation is what differentiates humid continental hot summer climates from other microthermal climates. Here we have humid continental mild summer climate, and in this climate zone, precipitation is less than the hot summer regions to the south, but the heavier snowfall is important to soil moisture recharge when it melts. And then we have our subarctic climates. Farther poleward, seasonal change becomes greater. The short growing season is more intense during the long summer days. This climate graph represents the subarctic cool summer climate, and the subarctic climate with very cold winters would only be found in Russia. Here we see the polar and highland climates, and the principal factors that cause polar climates include a very low sun altitude even during the long summer days, extreme day length between winter and summer, extremely low humidity, which produces low precipitation, and a surface albedo impact from the light-colored surfaces of ice and snow that reflects substantial energy away from the ground and reduces the net radiation of this area. And the final category of climates we'll be discussing is the dry climate. The Earth's dry climates cover broad regions between 15 degrees and 30 degrees north and south, and they occupy more than 35% of Earth's land area, so they're the most extensive climate over land. The dry climates are the only climate type in which low precipitation causes permanent moisture deficits, and they're subdivided into arid deserts and steppes. Deserts have greater moisture deficits than steppes, but both have permanent water shortages. These desert and steppe regions are biologically rich environments, but they are prone to long periods of drought, so they require special adaptations for plants and animals. Okay, that's it for this video. I'll see you in the next one.